Okay, hello everyone. So we are starting a new topic today, electromagnetic waves or EM waves, shortened form. So let's see what do we have under this main topic. So we'll talk about how to produce electromagnetic waves or electromagnetic radiation. This is pretty much the radiation around us. Um, we receive radiation from sun in terms of light and many different other waveforms, X-rays, ultraviolet, gamma rays. So there's so many different types of electromagnetic waves or electromagnetic radiation. Um, the mobile phone you use, it communicates with the signal tower using EM waves. TV signals, radio signals that come through space, that's electromagnetic radiation. The remote controller you use, to change the TV channels kind of stuff, that's EM radiation. The microwave oven that cooks food inside, or warm the food inside, that's another type of electromagnetic radiation. X-ray imaging. So there's so many applications. It's all around us. We call it EM waves, EM radiation in shortened form. So let's see so how to produce them and some important set of equations. Even though we don't go into any details at this point, I want you to know that at least the name. James Clerk Maxwell came up with this unique set of equations to describe the behavior of electromagnetic waves or radiation. And then we'll talk about the speed, one particular equation that deals with the speed of EM radiation, and a little bit about light and other different types of radiation. Measurements, historical measurements, energy, radiation pressure, in the conceptual level, and more details about wireless communication. So these are the topics we're going to discuss. This chapter doesn't have much mathematics in it, only like one or two equations. It's mostly conceptual. So I might ask you to do a lot of background research. Okay, all right. So let's move on. Production of electromagnetic waves. Now again, you have a basic idea what are these waves we are talking about, right? The light, the visible light that comes from the sun, from the street lamp, or inside the building, there's light bulbs. That visible light is electromagnetic radiation. Why do we call it electromagnetic? Because these particular waves, it's a combination of a changing electric field and a changing magnetic field. So when electric and magnetic fields change together in a particular order, the direction of these fields has to be perpendicular to each other. When they change, they kind of recreate each other over distance. So you have let's say you have some machine that producing a changing electric field and a changing magnetic field. So near vicinity of that machine, there are two fields changing, but they can recreate each other. The changing electric field can create a magnetic field, the magnetic field can create an electric field, vice versa. So, and these two together can propagate through space. We call it electromagnetic radiation or electromagnetic waves. So let's see what the slide says. Yep, so pretty much the same thing. So pretty soon we'll take a look at some diagrams. Okay. Alright, so how do we produce them? Oscillating charges will produce electromagnetic waves. So this is the very basic level, charged particles like electrons, protons. Oscillating means moving. Let's say we have an electron, a charged particle. If it is stationary, all it has is an electric field around it. Right? You know that it's actually pointing towards it, an electric field. So if you have a proton, there's an electric field around it. If this proton is moving, or if the electron is moving, now we have a charged particle that is moving. So the proton is moving with some velocity. Now it has this electric field moving with it, right? Electric field also moving. Plus, it will have a magnetic field, the B field around it, right? These are vectors. If the charged particle is moving, there will be a magnetic field around it. So we have a moving electric field plus it carries a magnetic field with it. This is stationary. So stationary means only electric field. Now if this charged particle is oscillating means back and forth movement. So this proton is going back and forth. So we have the electric field going back and forth. We have a magnetic field going back and forth. You know that the changing magnetic field can produce an electric field, electricity, right? The constant magnetic field can't. Remember the transformer we talked about the other day? When you have a change in magnetic field, it induces electricity in the secondary coil. So change in magnetic field can create electric field. So when you have an oscillating, that's the whole point, oscillating. There's a magnetic field changing, that creates an electric field which is oscillating, that creates a magnetic field which is oscillating. So likewise we have the two fields recreating each other. So that way the two fields can propagate through the other. That means at some distance from the charged particle you can measure changing electric and magnetic field. That means this wave something has propagated, right? Something has moved through the space, and we call it an electromagnetic wave or electromagnetic radiation. So here in the diagram what we have is there's this conductor, it looks like a rod, and it's connected to a battery. So when the current is going in one direction, there's charged particles moving. And if you can flip the direction, if you can switch the direction, the charges are moving in the opposite direction. So you have a changing electric field, creates these circles looking waves. That creates magnetic field, and then this thing can propagate throughout the space. So what do we do? Instead of a battery, instead of a regular DC battery, you put an AC generator. So that creates back and forth current, right? Back and forth voltage. So the electric field is going back and forth, the magnetic field is going back and forth, and they're going to be perpendicular to each other. So near the generator you will have electromagnetic radiation produced by the antenna. Now these kind of things we call them antennas. These conductors that connected to an AC generator. Far away from it, you see that we can make measurements, we can detect changing electric and magnetic fields. That means the wave is propagating. And this is how we receive radiation from the sun. Sun is so far away, billions of miles. What is oscillating inside the sun? Right? There is no like a mechanical generator or anything. It's charged particles, mainly hydrogen, mainly ionized hydrogen. So these hydrogen atoms, these essentially protons, right? Ionized hydrogen means hydrogen without an electron, that's a proton. So because of their kinetic energy, because of the heat, the kinetic energy, they oscillate, move back and forth. So they create these E and B fields, and that produce this radiation. We use these kind of wiggly lines to indicate radiation. So that's how we get light or any other radiation from the sun. So even though they appear like circles near the source, like let's say if this is a proton, so it's going in every direction. So if we call these wave fronts, if I connect equal looking points of all these waves moving outwards, we call them wave fronts. They're actually circular fronts. But when you go far away from this, the circle become bigger and the radius become bigger, so they appear like straight lines. So from a distance observer, you feel like parallel lines coming towards you, so you can draw arrows pointing parallel like this. Near to the charged particle, the arrows will be pointing away from it, but when it comes to a far away observer, somebody over here, they're more like straight lines, right? So we can say that the light from the sun falling on Earth is going to be parallel. These light rays are parallel, so that's why we consider them as parallel light, parallel rays, because they're so far that the wavefronts have almost become straight lines. Okay. All right. Let's move on. So here's a 3D diagram showing that this oscillating electric and magnetic fields, they're perpendicular to each other, they're recreating each other. So electric field is moving in the y direction, up and down. Magnetic field is moving in the z direction. As a result, the wave moves in the x direction. So even if you disregard the direction, what you need to know is the two fields, electric and magnetic fields, need to be perpendicular to each other, and the result goes in the third direction. So over here I have copied the link. I'm not going to click it right now because it's going to increase the length of the video a lot, but just click it when you go through this. This is an animation. It will show you much better details about how these things change. Okay, let's move on. So here's our first equation. The speed of this radiation. Now electromagnetic radiation can be visible light, can be X-rays, it can be gamma rays. This is gamma. It can be microwave, ultraviolet, infrared, microwaves, radio waves, TV signals, all these electromagnetic radiation. Now remember, sound is not part of this, right? Sound waves are different. They do not generate by moving oscillating charged particles. Sound waves are generated by different mechanisms, like a moving film or a diaphragm, something that some physical object has to move back and forth inside the atmosphere. So that moves the atmospheric particles, like gas particles, molecules, oxygen, nitrogen, those particles. It moves these particles back and forth. That's how the wave propagates. These things, electromagnetic radiation, they do not need a medium. So no medium. Right? It's just pure radiation, pure energy. There are no particles moving. And then the speed, how fast they are traveling, depends on what kind of medium it's traveling through. So when I say no medium, means it doesn't need any material to generate. It can go through can go through vacuum, it can go through certain mediums, like we know that light travels through air, it travels through water, but it doesn't need a medium. That's the point, right? Even without a medium it can travel. When it comes to sound, it always does need a medium. It cannot travel through vacuum. It needs either air to travel through or some kind of solid, like it will travel through, railway tracks, goes through that, goes through water. It needs some kind of medium to travel through, right? It needs molecules to oscillate. Electromagnetic radiation does not. As a matter of fact, it travels the best when there's nothing. It travels fastest through vacuum. When there is a medium, if there is a medium like atmosphere or water, it slows down. So what's the speed? Speed is given by velocity, or when it comes to EM radiation, we use the letter c as a standard. You might have seen this somewhere else. Speed of light. Light is also electromagnetic radiation. Is given by 1 over epsilon naught mu naught square root. Epsilon naught, permittivity. This one, permeability. What are these things? Permittivity tells you how much the electric field can propagate through the medium. Permeability for the magnetic field. So together, for a given medium, there is some permittivity and there is some permeability. The product, take the square root, take 1 over, that gives you the speed in meters per second. Now you can give it a try. You can do the math and see what the number is. For an example, we know permittivity of free space is 8.85 10 to the negative 12. We talked about this some time ago. Permeability of free space 4 pi 10 to the negative 7. We worked these things last week pretty much. Multiply these, apply in the equation, you'll get an answer. C is about 2.99 10 to the 8 meters per second. This is the speed of electromagnetic radiation through space, through vacuum, when there's nothing. And it is constant. All these, they're all electromagnetic radiation. They all travel at the same speed. We can take it as 3 times 10 to the 8. Good approximation, meters per second. Now, if you want to find the speed of light or speed of ultraviolet through, let's say, through glass, plug the numbers: permittivity of glass, permeability of glass. You'll find a number that's kind of close to this, but it will be less than this, right? All right, what's next? There's an electromagnetic wave, and okay, so now we have the speed. When it comes to a wave, there are certain wave properties. So let's talk about that. How do you represent a wave? We represent them using a sine wave, a sine signal. A wave is something, some form of an energy that changes, right? It reaches to a maximum, comes back to 0, goes to a negative maximum, comes back to 0, and then repeats. Over time, it repeats. So, by looking at this shape, we can define certain quantities, certain terms. This height to the maximum is called the amplitude. The length of a one full cycle from here to here, this is one full cycle, this length, it's called wavelength. Use the term lambda for that, measured in meters. Number of cycles, so this is a one full cycle, right? One wavelength is one full cycle. You can measure the wavelength from this starting point to this starting point over here, or you can measure peak to peak distance. That's also lambda, same distance. Time for a one full wavelength or time for one full cycle. Time for a full cycle. E equal, what do you call it? The time period measured in seconds. Number of per second, number of cycles per second is called the frequency measured in hertz. And we know that frequency is 1 over time, or time is 1 over f. So wavelength, frequency, wavelength given by lambda, amplitude, how tall this. So here's a wave with a high amplitude, here's a one with small amplitude, right? And also you can say here's a one with some wavelength, here's a one with shorter wavelength. This one have higher frequency, more cycles per second. There's an interesting, very simple relationship between the velocity and the wavelength and frequency. It's given by V equals f lambda, or lambda f. I like to call it V equals f lambda. Okay, so V equals f lambda. This is the equation that gives you a relationship between the speed, the frequency, and lambda. This works for sound as well, sound waves, and for EM radiation. Now, because we have like another standard that we use the letter C for speed, we can modify this just for electromagnetic radiation. We can say C equals f lambda, right? Remember this in meters per second. This is hertz, this is meters. Okay, let's see what else. Electromagnetic spectrum. What is spectrum? When we list all the known different waves according to their lambda or according to their frequencies, we call it electromagnetic spectrum. Now, the diagram is a bit small. Let me see if I can make it bigger. Alright, so here you see that the bottom row, all the frequencies, they are increasing to the right, starting from 100 going all the way to 10 to 20. At the same time, wavelength is decreasing. Why is that? If you look at this equation, C equals f lambda, C is a constant, right? This is 3 times 10 to the 8. This is a constant. Speed of this radiation is a constant. So if f is increasing, lambda has to decrease. So small frequencies will have large lambdas, means these waves are longer. Higher frequencies, the lambda getting shorter and shorter. Okay, so let's go back to the diagram. See, low frequency, long wave radiation, mostly radio waves, 60 hertz AC current, the household electricity, then AM, and then FM radiation, FM waves, that those radio channels mostly you will prefer to listen. That's the nowadays choice, FM. I'll talk about these acronyms. AM stands for amplitude modulation, FM stands for frequency modulation, TV, you all know that, that's television. And then comes cellular, satellite TV, comes the infrared radiation. So after infrared comes the visible light region. So this is the very narrow, limited frequency range we humans can see. Compared to the rest, you see that it's a very tiny, narrow band, short range of frequencies. So visible light starts from red. Just before red, we have infrared, and it ends with the rainbow colors, ends with violet, and just after we have ultraviolet, that is like above violet. And then comes X-rays, gamma rays. So the most highest frequencies that we have detected falls under gamma rays. Another thing to remember is with increasing frequency, the energy of the radiation increases. So that's why we say that X-rays, gamma rays are more harmful. Ultraviolet can be harmful to our eyes if you directly look at sun. There are different radiation that respond to different human tissues, right, or human cells. Like skin, infrared can be bad for skin, also ultraviolet. Visible light is pretty much okay for us. Our bodies, it's just the eye creates a sensation of vision, but other than that, it doesn't do a damage to us. Doesn't do a damage to our skins. But anything on the either side of the visible light, infrared, microwaves, or the other side, ultraviolet, X-rays, gamma rays, can be harmful to us. It can be harmful to our skin, can be harmful to our eyes, the hair, all that. Radio waves, TV signals, again, they can just pass through us, but they don't interact with the stuff inside our body. Like they don't interact with the not much with the water inside, the cells inside. So they're kind of okay. Microwaves are not. Microwaves have the same oscillating frequency, like the frequency as the water. So that's how you can cook food using microwave ovens, because they can increase the kinetic energy of water molecules that heats it up, right? So the same way, if it penetrates inside through the skin, that can mess up with the water inside the body. So that's why it's not advisable to be on the cell phone all the time. Keep it next to your ear, and it's pretty close to your brain. So use the speakerphone or some kind of wired headset, not a wireless one but a wired one. Wireless headsets, again, if it's using Bluetooth, it uses microwave, so same thing. Okay, so let's put this back. Alright, what else? Okay, so let's do a quick math problem. Examples. Calculate the wavelength. So we have question number 1, 60 Hertz EM wave. So this wave has a frequency. So frequency is 60 Hertz. So anything given using Hertz means it's a frequency. Asking the wavelength, asking lambda. So what do? We use this equation, C equals F lambda. If it is electromagnetic, we put 3 times 10 to the 8 over here, equals 60 times lambda. So what is lambda? 3 times 10 to the 8 over 60, so 300 times 10 to the 6 over 60, yep, 1, 2, cancels out, 5, so 5 times 10 to the 6 meters. Pretty long. 5 times 10 to the 6 is 5,000 times 10 to the 3. So it's like 5,000 kilometers, right? It's a pretty long wavelength. Like one wavelength can go from one end of the earth to the other end, that long. So you guys work on the other 2 examples. Second one says MHz megahertz, and the other one is visible light. So you can have an idea how the length of the visible light, pretty small in the nanometer range. So I'll give you the answers. B is 3.22 meters. C is 6.33 times 10 to the negative 7 meters. So see whether you can get these answers. Okay. Alright, moving on. Cell phone antenna. The antenna of a cell phone is often 1/4 wavelength long. That means if the wavelength the cell phone is using, if it is 1 meter long, if that's the length of the wavelength, the antenna has to be 25 centimeters long to have a good reception, and that's not practical. Your cell phone with a 25 centimeter long antenna, it's like 1 foot long antenna, that's kind of weird, right, to walk around with it. So these cell phones have short antennas inside. If you have seen the old-fashioned ones, I'm talking about two decades ago, the antenna was outside. It's like something that you can pull out, and then that gives you good signal. But with increasing technology, they found ways to keep the antenna within the phone, inside, embedded, so it's not visible to outside. And so it says the particular cell phone has an 8.5 centimeter long straight rod as its antenna. I estimate the operating frequency. So do the math and see whether you can figure out the answer. The answer should be around 880 megahertz. Okay. Alright, so and then go back to the spectrum and see where this frequency what is this frequency is. I'm sure this is in the microwave range. Okay, let's take a look at it real quick. 880 megahertz, 880 10 to the 6. So it is 8 times 10 to the 8. So yep, it's kind of around microwave range. That's for the cell phones. Okay. Phone call lag time. Alright, so you make a telephone call from New York to a friend in London. So here's the Earth. You are here, and across the this is supposed to be a person. Across the Atlantic, you have a friend. Estimate how long will it take for the electrical signal generated by your voice to reach London. So when you speak into the phone, your voice signal, that's a sound signal, it gets picked up by the microphone, converts it into an electrical signal, gets amplified, gets into a circuit that converts into a signal that can be transmitted. So that electrical signal becomes an electromagnetic radiation. Electrical signal itself won't travel that far, right? It has to, so this signal, actually something called the modulation, they mix it with a carrier frequency, a carrier signal that can travel through long distance. Again, the signal doesn't go from your phone to all the way to your friend. It goes from your phone to a signal tower. So this signal tower will pick it up, and then it goes to a signal station, the processing station. That's all in, like if you are a Verizon user, it will go to a Verizon station, and from the station it goes to a satellite, communication satellite. The solar panels of the satellite has an antenna waiting to get the signal, and then it has another antenna, relaying antenna, to transmit back to UK. So here's a receiver station, goes to the tower, from the tower goes to your friend. Inside the phone, it will remove that carrier signal from it and then isolate the voice signal It's an electrical signal, goes into the speaker. Speaker converts this electrical signal into a sound signal, sound wave, and then comes to you. So whole thing doesn't take much time. It says that the satellite is 36,000 kilometers above the ocean. Okay, general knowledge question. What kind of satellite is this? There are low Earth orbit LEO satellites, medium Earth orbit MEO satellites, and then geostationary satellites. What kind of satellite is this? At this altitude and for telecommunication, it has to be a geostationary satellite. That means, I'm going way off the topic, here's the Earth. There are certain satellites that just move around the Earth. While Earth is rotating, satellite is moving. So mostly like weather satellites kind of stuff, or spy satellites, military satellites. And then there are satellites called geostationary. So they rotate with the same angular frequency. Geostationary. The Earth rotates 10 degrees, the satellite also rotates 10 degrees. So it's always hovering above the same point. Those are the communication satellites. And they're pretty important. This idea was mostly, I would say, not proposed but championed by a visionary named Arthur C. Clarke, a famous science fiction writer. He's a big proponent of placing geostationary satellites for communication. If you have read this 2001 Space Odyssey, and he has a series of these books, pretty interesting stuff. Okay, so yeah, try this problem. These distances are short, but here you have 36,000 kilometers going up, and then 36,000 needs to come back, traveling at the speed of 3 times 10 to the 8 meters per second. Even if we disregard all the processing time, I want you guys to do the math. It takes about 0.24 seconds for this whole thing from here to your friend, because it's a round trip, right? Going up and has to come back. Let's forget about the processing time and the time from you to the tower to the station and all that. So with the current technology, it takes about, not the current technology, the speed of these signals, takes about 0.24 seconds. That is a noticeable delay, little noticeable. Imagine sending a signal to the rover that's on the planet Mars right now. There's a little helicopter with it, right? So that's like millions of kilometers away. So that takes a lot of time for us to send a signal and to hear a response. Alright, moving on. Measuring speed of light. This is a very interesting historical experiment done by Michelson, I think. Yeah, Michelson actually, not Michelson. I think his name is Arthur Michelson, or Michelson, something like that. A renowned scientist. This is a very painstaking process. Speed of light, it's not easy to measure because it's so fast. The laboratory equipments, even we have today, it has to be really, really sensitive. So this is like hundreds of years ago. He came up with this idea. I'm not going to go into detail. He has a light source. He has a rotating mirror, 1, 2, 3, 8-sided mirror kind of thing. So the light comes in, reflects, and the second mirror, stationary mirror, this is 35 kilometers away. So you have to have these large distances to get some accurate answer. So Mount Wilson, so these two places were on top of two mountains. So on like a clear days, you can clearly, and you will be able to see the other mirror. So light reflects from that, so it's a 70 kilometer path, and then comes to the observer, and then he's rotating this. So only at particular angles the light goes to the observer. So by knowing the distance and the rotational speed of this thing and the angles and all that geometry, you can figure out the speed of light. And using this old technology, I think this is, I don't remember the year. Using this limited technology, he was able to calculate speed of light pretty accurate to the current accepted values. Okay, so this link, if you're interested, that goes into details of this. Okay, so yep, here's the speed of light with more decimal points. Okay, so I'm gonna stop right here, and the rest we'll discuss using another video. Right? Thanks.